Hello, everybody. Welcome to the seminar series, actually young seminar series. I'm happy to hear a lot of you here. And today we have 3 talks of great speakers. And the outline is that we first will listen all talks, and then in the end we will have questions, if of course you have it. Or you can put your urgent questions in the chat and we will then forward it to the speakers. And Christina will introduce you to our speakers. So Christina.
Yeah, thank you, Sinia. And hi, everyone. Our first speaker today is Jasone Ramírez Ayerbe, a predoctoral researcher at IMUS, the Institute of Mathematics of the University of Seville, here in Spain. And if you want, Jasone, you can start sharing your content. She's going to present us the work entitled A Unified Approach to Counterfactual Explanation by Means of Mathematical Optimization. The floor is yours, Jasone.
Okay, thank you so much for the presentation. This is a joint work with my supervisors, Emilio Carrizosa and Dolores Romero Morales. So first of all, I'm going to talk about a little bit about the importance of interpretability in data science, and then I'm going to talk about contrafactual explanations for different machine learning models, and also not only individual level contrafactual explanation, but also at group level. So interpretability in data science, due to the increasing use of complex machine learning models, it is more and more important nowadays to be able to interpret them. And indeed, the EU imposes the so-called right to explanation in algorithmic decision making. That is when an individual is subject to a decision made by a machine learning model. That individual has the right to know the reasons of the decision that machine learning model has made. So not only does accuracy matters, but also interpretability and transparency. There's a lot of someone says that they cannot see the presentation. Is it?
Maybe you can refresh the page.
Okay, that's not my problem, right?
Right.
Okay. There's a lot of methods that try to interpret different complex machine learning models like LIME and CHAP. And also there's some works that study the fairness of the machine learning models, because the black box models should not discriminate against specific groups of people. And also there's what we call counterfactual explanations. That's what I'm going to talk about in this talk. So what are a counterfactual explanation? Suppose that we have a person that would like to apply for a loan, and to reject or to accept that appliance is made by a black box model. And these black box models makes the decision to reject the appliance. So that person asks why. In that case is when we calculate the counterfactual explanation for that specific person and for that model. So we would have the original features of that person, and we would give that person the changes that would have to be made in order to change their prediction. So a counterfactual explanation would be, had your salary been 30K instead of 25, and had you had two accounts open instead of 4, then your loan would have been accepted. So given a multi-class classification model with K classes, given an individual X who has been classified with a given model in class K, we ask what are the changes with minimum cost that causes that individual to be classified in another class. So this problem has been already studied in different ways. Instead of that, we can see using integer linear programming, a lot of them using metaheuristics and, for example, genetic algorithms or graph-based algorithms. And also, the majority of them are only valid for specific methodologies, like differentiable models or tree-based models. So our proposal is a unified approach to contrafactual explanations for specifically score-based classifiers. And we're going to solve this problem using a mathematical optimization. It's going to be applicable to multi-class classification models like logistic regression, support vector machines, random forest, or XGA boost. And also, that we find is kind of new, we're not only going to give individual level explanation, but also group level explanations. So let's define the optimization problem for the contrafactual explanations. So we're given, first of all, a score-based classifiers. It's going to be defined with the score functions for each class. We're given an instance with predictor vector x0, and that instance is going to be classified by the given model in the class whose score function is the maximum among all of them. We're going to suppose an actionable feature space. That is the space where we can move the different features. It's going to be basically a polyhedron with some integer coordinates. For example, the upper and lower bounds of the features, and also to define which features are categorical and which are continuous. And also we are going to have a cost function that's going to measure how difficult it is to change each feature. So our contrafactual explanation for x0 to be classified in class K star would be minimizing that cost function, subject to classifying our instance in class K star, that is, imposing that the score function of K star has to be the maximum among all of them. So we're going to specify this problem for different models. First, I'm going to start with additive tree model. So we're supposing that the additive tree model is already given. So we have the structure of the additive tree model is data for us. So first of all, we can consider an additive tree model as a score-based classifier. Suppose in this case that all the trees have the same weight. And so for that instance, the score for class B would be 2 and the score for class A would be 1. So that instance would be classified in class B. And so we can apply our problem to this model. As we've said, we have a lot of data already given from each tree of the additive tree model. We have the weight of each tree, the set of leaves, also basically the structure of each tree, the threshold value and feature used in each split, and also to define the score function, we have the subset of leaves in the tree whose output is class K, each class. And so that's the data. Or decision variables is first of all the contrafactual explanation. And so we can define the score function for class K as the sum of the trees that predict X in class K. But we're going to add to our formulation a binary decision variable that's going to be set. And set is going to indicate whether the contrafactual instance X ends in a leaf of a specific tree. Basically, set what's going to indicate is the path that the contrafactual explanation in which path the contrafactual explanation is for each tree. And so we can define the score function in a linear way using these decision variables. We are now defining the optimization problem using this data and the decision variables. So we're minimizing the cost function. And so the three first equations are the good definition of the binary of the decision variables set. The first two define all the paths of the tree, and the third one is imposing that obviously each instance can only end in a leaf for each tree. And we also impose our contrafactual explanation. If anyone stopped seeing the presentation, please refresh the the page because I think it's not something I can change. And also we impose X to be classified in K star. And yeah, this is the formulation for a problem for additive tree models. We are going to see a particular case when we want to minimize not only the number of features change, but also the sum of the square deviations. In that case, we can linearize the L0 norm, and we obtain, in this case, either a mixed integer linear programming model or a mixed integer convex quadratic model with linear constraints. Let's see some computational experiments. We're going to use the Boston housing datasets. With these datasets, using different features of houses. We classify an instance in the positive class if the value of the home is higher than the median value, and in the negative class if the value of the home is lower than the median value. We construct a random forest, and we impose some time limits. So contrafactual explanation for one instance would be what we can see in the image. In this case, we had an instance which was classified in the negative class, and we want to know the changes to be classified in the positive class. We can see that the changes make sense. For example, in this case, RM, that's the value of the number of rooms. It says that if we want the home to be valued more, then we have to increase the number of rooms. We can not only see one for one instance, but here we can see in this heat map the contrafactual explanation for 10 instances of the dataset that were classified in the negative class and to be classified in positive class. Something to notice is that if we calculate the class probabilities, the original class probabilities returned by the random forest, we can see that it makes sense that if we have an instance like instance number 1 that was classified in the negative class with a probability of near 60%, then that instance has to change only one feature, whereas instance 3 that was classified in the negative class with a higher probability with 84%, then that instance has to make more changes than the other one. And so here we show different contrafactual explanation using different cost functions. Like here we are only minimizing the number of features change. Here is the sum of the two norms, and here we can see if we minimize only the square deviations. So this problem that has been formulated for additive G models can also be formulated for linear models in a much easier way. For example, for logistic regressions, it is easy to see which the score functions are, and also for superfactor machines. I don't have much time, but we can also define in the same way the score functions. We obtain the same kind of optimization problem. And we can see also the contrafactual explanations for logistic regression and support vector machines. In this case, both of them are linear models. They are not the same, but they're really similar. And at last, I want to talk about group level contrafactual explanation. What we've seen until now is the contrafactual explanation for an individual, but suppose we have a group of individuals, they all would like to apply for a loan, and the majority of them are denied that loan. And so they ask why. We could do the same as before and tell each one of them their contrafactual explanation, but we can also ask what are the changes for maybe 50 of them to be able to have the loan. And so what we're trying to see is not only the behavior of the model towards an individual, but the behavior towards group of people. Maybe people that kind of share the same features. And so in this case, if we want to generalize the model for groups of instances, we have to decide not only what the contrafactuals are for the group, but also which individuals of the group are going to change its class and which of them are not going to change their class. We generalize the optimization problem for additive tree models, but also for group. In this case, each variable has an additional index indicating which individual are we talking about, and also the cost function that we use now is also made to look for the changes made as a group, and so we do not minimize the yield-zero norm for each individual, but we minimize the number of features that are changed in general in the group. And we can linearize all of the formulation. And so we obtain, for example, this kind of contrafactual explanation. We have chosen instances that had a criminality above the median value, and we could see that generally these instances were classified in the negative class. And so we ask, what are the changes to be made for 50 of them to be changed to the positive class? And so we see what had to be done for all of them to change its class, and in the right image we see what would have to be done in order to change 50% of them. So just a summary, what we post in this talk is a unified approach to counterfactual explanation. We have used mathematical optimization. We have seen that's applicable to diverse score-based classifiers, some linear models and additive tree models like random forest XGBoost and linear models. And also we have seen that we can calculate contrafactual explanation at two levels, individual and group. And future work that can be done is first improvements to the formulation as we some big M constraints. Also, what happens if we have uncertainty in the instance in the original instance, and also if we can have some robustness across models. As we've seen, the contrafactual explanation for linear models are quite similar, but not for additive tree models. And that is all. Thank you so much. I think I'm on time.
Yes, Jasone. Thank you very much for your very nice presentation and for being on time. Just to recall the audience, we are going to let the questions until the end when all the speakers gave their presentation. So our next speaker is Gabriele Iommazzo. He's a PhD student from the Polytechnique Institute of Paris in France, and the work he's going to present today is entitled Optimize to Learn to Optimize, Getting Down and Dirty. So I hand over to you, Gabriele.
Hi, everybody. First of all, can you see the presentation, the slides?
Yes, we can see it. Recall the pointer.
Yeah, I have it. It's here. You should be able to see it as well. So, hi, everybody. Okay, I have my stopwatch. Hi, everybody. I'm Gabriele, as Christina said, and so this work I'm going to present is the fruit of a joint collaboration between École Polytechnique of Paris and Università di Pisa, which here are represented in the slide by my three supervisors, Claudia, Antonio, and Leo. And since Antonio already introduced the topic of this talk with a quite nice overview in this very series of seminars last week, I will go very fast on the introductory part, and I will try to delve deeper into the details, into the implementation-related stuff. So, okay, changing slides. So first of all, what does it mean optimize to learn to optimize, and why part of the title was the algorithm configuration problem? So mathematical optimization is notoriously and infamously hard to solve. It's so hard that there is no such thing as a unique algorithm that is good for everything, for every problem. So you normally use software complex software which contains many algorithms that are made to work and interact together, to collaborate together, to solve specific instances in different problem classes. Now, optimization solvers come with default configurations, but the problem with default parameter configurations is that they may be, and they often are, suboptimal on specific instances. So this phenomenon requires that you set out on a journey to tune the parameters of the solver and to find the best values for solving the instance at hand. However, this tuning is often performed manually, meaning that it takes a long time, and it's very hard because the space of all the possible configurations is huge. In fact, well, many solvers expose hundreds of parameters. So in the last years, in the last, I think 20 years or something, there has been a development in the algorithm configuration community to try and solve this problem. So the components of the algorithm configuration problem, the ACP, are the following. A is a target algorithm. C is the set of feasible configurations. The problem to be solved, represented by a set of instances, is pi, and the performance function of the target algorithm, that is to say, the outcome of running the target algorithm for a specific instance and for a specific configuration, is p. Choosing the performance function is not straightforward. You may choose to measure the time taken to find a solution, or, for example, some measure of the quality of the solution found within a certain time limit. But in general, the definition is as follows. If I give you a target algorithm, an instance bar pi to solve, and the performance function of the algorithm, you have to return, you have to find the algorithmic configuration C star that is capable of providing the optimal performance of the target algorithm for solving that instance bar pi. This is basically the algorithm configuration problem. I will skip this part. It was already introduced by Antonio. And what I care to say is just about this classification of, well, there are many classifications of algorithm configuration approaches, but this is, I would say, the most important one, the one which distinguishes between per instance approaches and per problem approaches, where per instance approaches define the best configuration and, well, as well, the best one for each specific instance. So the best configuration changes in function of the instance, whereas per problem approaches, they define the best configuration as a good one for a set of very similar, very homogeneous instances. And what we do is a per instance approach. So we want, given a certain instance that we want to solve with the target algorithm, we want to find a good configuration for that instance. Now, I will also skip this part and tell you about the pillars, the assumptions on which our methodology relies. So we assume to know how to represent the set of feasible configurations. For us, the set of feasible configurations is composed of binary vectors of Q components, and the conditions on the parameters are expressed by linear constraints. So this is a MILP representation. We also define an encoding of each instance by a vector of m real components. This is the instance features. And also we choose to measure as performance function the integrality gap achieved by the target algorithm, in our case by the solver, within a fixed time limit. So our approach is twofold. In a first phase, we want to learn the behavior of the solver. And in a second phase, with this information, we use this information in a mathematical program, in an optimization problem, to find the best configuration for a given instance. So in the first phase, we use supervised machine learning to learn an approximation, which we call p-bar, of the performance function p. To do this, we use a training set where the training inputs are this iota, which is the instance features of the instance, the encoding of each instance, then C, which is the encoding of a configuration, and the recorded performance function for that instance and that configuration. Then how do we use this learned information? So we take the predictor that we learned and we translate it into mathematical programming terms. This gives an objective function and some constraints which become part of a larger mathematical program, which we call the CSSP, the Configuration Space Search Problem. And by the way, the phase is the PMLP, the Performance Map Learning phase. The CSSP is solved for a given instance by bar to find the best configuration C star for solving that instance with A. What does it mean, solving the CSSP? It means minimizing. It means finding the minimizer of this problem. Why? Because P bar estimates the integrality gap, and the smaller the integrality gap, the closer you are to the optimal solution of a certain problem. So the implementation, this is a very generic form, but the actual implementation of this program depends on the formulation that you choose to translate, to represent the learned PMLP predictor. So we will have linear programs or nonlinear programs, convex or non-convex, etc. I will show you two examples later. The constraints of this program are, well, of course, the constraints describing the set of feasible configurations, linear constraints, this C in C of A. And also, you may need some additional constraints to define the structure of the predictor. Then the produced estimation P bar appears in the objective function, and you want to minimize it. And the input of this program is, well, of course, a given instance. So more specifically, it's encoding the instance features and the coefficients of the learned model. So about the implementation, I will show you two approaches, two machine learning paradigms. The first one is support vector regression. I will lead the details for the questions, but basically we chose to test computational experiments nonlinear support vector regression using a Gaussian kernel, which gives this MINLP, this program, which is, well, clearly nonlinear because of the objective function, and non-convex because of what's inside the norm of this objective function. This is basically what is alpha. Alpha are the optimal dual Lagrangian multipliers of the dual SVR formulation, which is solved. B is another coefficient of the primal formulation of SVR, and gamma is a hyperparameter found by cross-validation during model training. This is the formula of a Gaussian kernel. It's basically a sum of exponentials, with the sum of exponentials. And the constraints of this program are, well, the MILP representation of the configuration space, configuration set. And for trees, I will do the same. I will leave the details for the questions. But basically, a tree is a graph where you have intermediate nodes and leaf nodes. Intermediate nodes have father, two children. Leaf nodes have one father, no children. And then, of course, you have arcs linking nodes. At the leaves, you have, at each leaf, you have a label, the label providing the approximation P bar of the tree. And at each intermediate node, you learn during training the optimal branching rules of the tree. That is to say, you want to select an input variable and you want to know whether a certain input for that variable has values less than or equal to a certain threshold or greater than that threshold. For us, an input is, again, a couple instance features, this iota, and configurations. So at our intermediate nodes, the branching variables can be feature variables or configuration variables. So with the CSSP, what we want to do is we take the tree learned by training, this T star, and we want to retrieve the subgraph T prime of T star. How do we do that? Well, when the CSSP is solved, we know the features of the instance pi bar, so we can prune the subtree T star in order to eliminate all the nodes branching on feature variables, and so T prime in the end it only contains nodes branching on configuration variables and leaf nodes. So what we want to do is we want, and this is expressed by this CSSP, which is a linear program, we want to find the path from the root of the tree to one of the leaves of the tree in order to minimize the label chosen, the label which we arrive on, the label of the leaf which we arrive on. We do this by using binary variables, these y variables, which basically tell you that at a node v, if there's some flow incoming, that is to say, some flow from the predecessor of the node v and v, then the variable y is 1, otherwise it's 0. And then we have some constraints. These constraints tell you that if there's flow entering a node, there must be flow going out of the node, either to the left or to the right child, because a tree is a binary graph. And then these constraints basically make sure that the partitioning rules of the tree are respected. What is C? C is a configuration variable. So how do you build your path? Well, you set C either to 0 or to 1, because as you recall, maybe the configurations are binary vectors. So these constraints tell you that if you set C to 0, you go left, basically. So your path proceeds leads you to the left from a node to its left child. Whereas if you set C to 1, you have, that means go right, and then you build your path from the root to one of the leaves. So as you saw, different machine learning predictors yield a different CSSP. We have seen that in the SVR case, we have a non-convex MINLP, and whereas in the decision tree case, you have a linear program. What does this mean for the CSSP? How difficult is it to solve each associated CSSP associated with the learned machine learning paradigm? And also this gives you a trade-off between producing a predictor that has a high accuracy, prediction accuracy, and solving the CSSP quickly. Why? Well, because potentially by producing a predictor which is very accurate, you also have a very complex prediction, and so its mathematical programming representation in the CSSP may make the CSSP very, very hard to solve. And so to start, this is exemplified in this table. This one, sorry. Okay. Basically what we do is we check how many times the CSSP solution, which we call C star, is exactly a global solution of the CSSP. So as you can see, in the case of decision trees, which are solved by the solver Cplex, whereas the CSSP for SVR is solved by the solver Bomin. In the case of decision trees, you always manage to find a global solution of the CSSP, so a global minimizer configuration. Whereas in the case of support vector regression, this is not always the case. You manage to find a global solution in more or less 90% of the cases. And here we measure the gap. So each time you find a local solution, each time the CSSP is solved locally, we want to know how far we are from the best solution. The gaps are quite tight. But what is really interesting to notice about this table is this time column, which just tells you how long it takes for the solver to solve the CSSP. And it's, well, decision trees have clearly the edge here. It takes, well, basically 0 seconds to solve the CSSP, which is a linear program. So nonlinearity has a role in this, whereas the SVR is way slower, relatively slower. And also you can notice how, so what we did in our experiments is we tested different feature selection scenarios, and we in the PMLP, and we tested how applying a more aggressive or more gentle feature selection influenced the results. So as you can see, when you have a very aggressive feature selection, meaning that Q, the number of configurations considered, is only 10, whereas in this case it's 23 when there's no feature selection, and in this case it's just 14. So as you delete, as you leave out some variables, solving the CSSP for SVR becomes easier, because of course you have less constraints and less variables to consider. So you go from 15 seconds for 23 configuration variables to 5 seconds for just 10 variables. Then in this, also in this and the following tables, you will see ES and OS. What is this? Well, ES, it stands for in-sample instances, and OS for out-of-sample instances, where in-sample instances are used to train our machine learning algorithm, whereas out-of-sample instances are never seen during the PMLP phase, so they are never seen during training, and we use them to assess the generalization capabilities of our pipeline. Another interesting table is this one, where the only difference that you can see is this P of A, P of ML. Basically, what's the difference here? So P of A is, as I told you, the integrality gap achieved by the solver in a given time limit, which for our case was the solver which we decided to configure was Cplex, and the time limit was 60 seconds. What's PML? PML is the training is the output that we use our machine learning algorithm to approximate. So how do we obtain PML? Well, PML is basically obtained by taking P of A, the integrality gap, and then by processing it, by identifying some outliers, by deleting the outliers and substituting them, and by scaling what is left in an interval 0, 1. So this PML is what really our machine learning algorithms learn, and you can see how this influences the pipeline. So in these columns, we have measured W is the number of wins, the percentage of wins. W plus D is the number of wins plus draws, and W minus D is the number of wins whenever there is no draw. What's a win? What's a draw? When a win is given the CSSP solution, that is to say the configuration that we find by solving the CSSP, and given Cplex's default configuration, what we do is we measure the integrality gap P of A of the Cplex's solution and Cplex's the CSSP solution as Cplex's default configuration, and then we also measure for these two configurations. We also measure P of ML, and we measure the number of times that the performance of our configuration is better, that is to say, is less than that of Cplex's default configuration. We measure the number of times that our performance, the performance of our configuration, is less than or equal to that of Cplex. And well, as you can see, the results with PML, which is what we decide to approximate in the machine learning phase, are way better than the results with the integrality gap. And this tells us a lot, because it tells us basically that what we are optimizing in the CSSP is what we learned, and so we are doing better with what we learned that with other metrics. And maybe the last table, this one, and then I'm closing.
Gabriele,
in this table, we
just
yes, the last one.
you that 1 minute. Ah, okay, thank you.
Yes, really the last slide. So in this slide, you have we also take our configuration, the configuration returned by the CSSP, and Cplex's default configuration, and we measure the number of times that Cplex configured by both the CSSP solution and its default configuration is capable of finding a feasible solution within a given time limit. And in all the cases where a feasible solution is found, we measure the primal gap, that is to say the distance between the optimal solution of the problem and the optimal solution value and the best feasible solution found, and the dual gap, that is to say the distance between the optimal solution value and the optimal relaxation. And well, basically what you see here is that simplex is more robust. It always finds a feasible solution, whereas we do not always. And you can also see, and this is the nice part, that our gaps, when we manage to find a feasible solution, which is in more than 90% of the cases, our primal and dual gap are always better than simplex. And you can also see that generally decision trees are better at generalizing, that is to say they are better on out-of-sample instances than SVR, than the SVR model. And well, this is basically all. Sorry for being a bit late.
Thank you, Gabriele. No, it's okay. Thank you for your presentation. So we go now for our last speaker, Victor. Victor Bucarey López is a postdoctoral researcher from Vrije Universiteit of Brussel in Belgium, and he will talk about end-to-end decision-focused learning over combinatorial problems. I give you the floor.
Thank you, Christina, and thank you, Senia, for organizing this nice seminar, and also thank you, Dolores, for inviting me. Actually, I'm a postdoc researcher at the Free University of Brussels, here in Brussels, Belgium, but I'll be joining in a couple of months in our University back in Chile, so as an assistant professor, so I have to mention that. This is a joint collaboration with people here in the team at VUB and also at the KU level. This team is led by T.S. Guns, and also all this work is with Giant Temandi, Massimo Lamba, and some other collaborators from Italy, Michelangelo Dirigenti and Michele Lombardi. So the problem that we have been working on, it's this predict plus optimize for combinatorial optimization, also called known as decision-focused learning. And in this setting, we want to train a machine learning model. Oh, I forget that. I need to click here. So we want to train a machine learning model, given some features, and then this prediction, we want to use it in optimization problem. So for instance, we have a shortest path problem, and we want to have some estimation of the travel times on each edge. So a typical approach is to do a two-stage approach in which you first train your machine learning model using as a loss functions, for instance, minimization between the norm of the predictions and the true cost vectors. And after that, you use it in the optimization problem. So the problem here is that you are in this setting, or by using minimum squared errors, you're just considering each prediction individually, and you're not taking care about the optimization task that you will use your predictions. So in this typical two-stage approach, as I mentioned it, you have like a setting that you train your model, then you plug these predictions into optimization problem, meaning a MIP solver or any combinatorial optimization algorithm, and then you use that. So we observed that by training your model using this kind of errors, as you fit well the data, it's not necessarily true that you will perform well in your task. So the general question here is, can we do the training in order to perform well in an optimization task? Okay, so how do we measure how well do we perform in an optimization task? Well, the right concept to use here is the regret, meaning the excess of cost of doing some error in your predictions. So mathematically, we consider a combinatorial optimization problem with linear functions, and the space V can be linear, any integer or mixed integer feasible region, and we define the regret as the difference between the objective function when we optimize the predicted vector C hat minus the real cost vector. So we are measuring the excess of cost, the excess of cost of doing our predictions. So what is the problem that we want to minimize? Actually, we want to minimize, we want to find the parameters of the model, of the machine learning model, in order to minimize expected regret. The good thing about it is that, or the good or the bad thing about it is that it can be seen, this problem, as a bi-level optimization problem, in which in the objective function we minimize the average regret, and in subject to that each constraint will return the best solution when C hat is minimized, with the prediction is minimized. So what are the challenges here? So first, dark mean is not unique. So we need to make a decision of how we choose an optimal solution when the predicted vector is minimized. Secondly, if it's implicit, or if it's not implicit, it can have like an exponential size. And actually, if you do training with a typical stochastic descent algorithm, dark mean of F may be an NP-hard problem. So this is a not trivial problem to solve. So in the literature, what is done? So for instance, Grigas and El-Maktoub, in a super nice paper published this year in Management Science, they use a pessimistic assumption, meaning that their mean function in the constraint will return the worst regret solution. So to compute the regret in this context is hard, because you will have a tri-level optimization problem, because you will have a minimization on top level, but in the constraint you will have a double, another bi-level optimization problem. The optimistic assumption, on the other hand, is harder to, but it's easier to solve, but it may return ambiguous solutions. So let me show you this in the following example. So we have here a super simple LP, and two cost vectors, two observations. So I depict here in orange the two optimal solutions. And what about if we optimize this problem in an optimistic way? The optimal solution will be actually to predict always 0. Why? Because if we predict 0, each feasible solution will be optimal. Then the lower level problem will be the whole feasible region, and then by choosing the one that is better for the upper level objective function, it will select the true ones, but given some ambiguous or unuseful, non-desirable outputs. On the other hand, the pessimistic regret in the whole feasible region will select the optimal solution that will do the worst for the upper level problem. So for instance, if this is the true optimal solution, if C2, well, I'm not pointing here. You cannot see my pointer, or yes? Can you see my pointer?
Now we can see it. Yeah.
Ah, great. Okay, so if this is the optimal true solution, the pessimistic regret will compare it with the worst solution over all the optimal solutions when C hat is optimized. So in this case, it will be 0. So here the pessimistic regret, it will say, well, predict 0, it will give you a regret of 5. And in this case, you can avoid non-desirable solutions. So on the one hand, we have this optimistic regret that is quite easy to solve, but it doesn't give any information. And on the other hand, we have this pessimistic regret that is quite hard to solve. So this paper from Elmachtuf and Grigas, well, they define as a clever upper bound on the pessimistic regret, and it's convex also, so it's easy to solve during training. So they solve a convex combination of the real C and the predicted C. So it includes some perturbation during training to avoid abusing of equivalent solution at the moment of doing the predictions. And this is quite nice. And so when at the moment of training, well, how you can transform the standard stochastic gradient descent? Well, actually, the only thing that you need to change is at the moment of computing the gradient to backpropagate, you need to first do this transformation or to this surrogate class function, then to call a solver to solve the optimization problem at optimality, and then to use the subgradient to that solution to backpropagate. The problem with this approach in general that we need to solve at each epoch and for each batch one and maybe NP-hard optimization problem. So the literature in these last years it's dedicated just to see how to solve this problem efficiently, or how to do this training efficiently, and also by having also good quality. So the main approaches that are to solve some perturbations with a black box solver. So they consider this call to the combinatorial optimization solver as a black box, and they use this solution and then they backpropagate. Other branches related to do implicit differentiation of the KKT conditions, so they use LP relaxations, and that it has some information about the combinatorial optimization problem that is underlying. Also, there are some work that add some Montgomery cuts and other type of cuts to have a better representation of this. So basically, in the literature, they took the combinatorial optimization problem, they just solved the linear relaxation, and they aim to see that this is informative enough. So we took a different approach. So in this approach of instead of solving the combinatorial optimization problem out of optimality, but using a linear relaxation, you also need to call an LP solver at each iteration. So we focus in another approach. So we thought, well, actually, we have some solutions that are optimal solutions for some instances. So actually, they lie in the convex hull of all the integer solutions. So we can use these solutions as an inner approximation of the convex hull, and we can optimize there. So in the literature, they use a linear relaxation, so they have an outer approximation that can be good or bad, depending on the formulation. But we say, well, actually, the inner approximation can be more informative if we have a big enough sample of solutions there. The good thing is that we can replace the call to a solver by a simple argmax over a finite solutions. They can be used by any black box method, and that's it. So and also we can do some kind of pricing. So in the sense that we can, while we are training, we can search if we have another solution underlying on the convex hull that give us more information during our training process. Also, we add some on top of that, we introduce some probabilistic loss functions that, as I'm going to mention now, So this work is in our HK article that it was accepted a couple of weeks ago, and it will be released in some more weeks. So the contrastive loss, or this probabilistic loss, the thing that it does is like, well, it defines a probabilistic distribution over all the feasible solutions. So with set, here's a normalization factor that is untractable to compute. Then the loss function, it compares the true ones, the probability of the true optimal solutions with some noise that we can add. The good thing is that by maximizing this probability, this log likelihood, the normalization factor, it cancels out, and we can have like with some math, we can have a super nice form of loss function. So the algorithm looks like this with this solution catching the contrastive losses. It has two key elements. First one, it has a growing strategy that we implement the most naive approach. So we at each 5%, 10%, or 50% of the iterations, we call the solver in order to search new solutions. And their mean over the solution pool is just an argmax over a finite and tractable solution. So what are the results here? The results are quite good. So this black box and SPO catching is the Grigas method and the black box method that I mentioned before. And this one is one of the loss functions that we introduced. The good thing is that we can have very good outsample regret, but in reducing dramatically the solution times. Also, in this figure, and this is the last figure to finish at time. So we don't this figure shows that actually looking for solutions on the training instances seems to be enough. Actually, here I have 3 instances of a knapsack problem. So this is the 0, the 5%, and the 100% represents the frequency in which I call a solver to find new solutions, in this naive way of finding new solutions. And actually, for the simplest case, well, looking for new solution, it doesn't add any value. For more complicated one, to find only the 5% of the time new solutions, it's enough to have the optimal regret. So that's it. So in the conclusions, well, we have a new paradigm of training in this predict plus optimize context by using an inner approximation of the feasible region. Also, we introduce some loss functions inspired by noise constructive estimation, and actually these two concepts allow to reduce solution times drastically while not losing the quality of the solution. So that's it. Thank you very much.
Thank you, Victor, for a great presentation. I think we can start our questions part. So if the audience has any questions, you can just raise your hand, unmute yourself, and ask a question. So we wait your questions. Usually it requires some time for people to ask. I don't know, maybe I can just ask minor questions. I have a question to you, Victor. So I'm not familiar with this approach as you talked, and maybe you can introduce a bit. So is it a neural network you mentioned because you used the word epochs, or it's something two-stage approach for other operation research tasks?
Well, actually, the thing is that they use neural networks to train this, but actually this is an optimization problem when that you can, instead of minimizing the how well the prediction fits with the data, you're optimizing the how well you will do on an optimization task. But it can be done by with that neural network, or it's basically a stochastic gradient descent.
Okay, thank you. So, but small just example of applications.
Yeah. So actually, I rush a little bit. So
We have-
actually,
continue.
so suppose that you need to dispatch fireman trucks to, if you have an emergency, and you need to estimate what it will be the good shortest path. And I use the good shortest path is because you need to first have good predictions of what will be the travel times on each edge, and you will also want to solve this with the good algorithms and efficient algorithms that you have for shortest path. So the thing that we are doing is just to find the good estimations, not fitting well the data, but that you will regret the least. You see what I mean?
Yeah. I see you changed the objective function, so
Yeah.
you have some benefits. Actually, we have a question from Juan.
Juanmi.
Yep.
Hi, Victor.
Hi, Juanmi.
Very nice presentation. I have just one doubt to see whether I have understood your idea. Well, first of all, I guess that your methodology applies only if you have the parameter to be estimated is in the objective function, right? So that your pool of feasible solution is always the same, right?
Yeah, actually, yeah. So the reason here we don't have a matter of feasibility, but just a matter of optimality.
Okay, so but because the idea is that you have a feasible region in your combinatorial problem that you can explore beforehand, right? Like, because it's always there, it's always the same, right?
Yes, that's
So
the reason why this approach works well. Otherwise, you may have you have to store different feasible regions or approximation of the feasible regions. So it's a little bit more complicated.
Okay, I see. Then you maybe beforehand you have a pool of feasible solution, integral feasible solution, and then every time you come up with a new value of the parameter, you evaluate that parameter over that pool of feasible solutions.
Yes.
Right, and then in your algorithm, you said that you don't see so much difference when you increase the size of the feasible solution set. That this is what you said in the end.
Yeah, and this is quite reasonable during training. So if you're training and you include at the beginning all the solutions that belongs to these training instances, you may expect that the predicted cost vector will be one that are mathematically in the cone of the vectors that are optimal for this set. You see, so the only way to have more new points is just to going outside in one prediction of this cone. You see what I mean?
Yeah, more or less. I think so. But very interesting. Thank you for the presentation.
No, thank you, Juanmi.
May I ask Gabriele, because I have one question to Gabriele. So I've seen that you used SVR, so support vector regression, and decision trees.
Yes.
So just my question to you, what kind of motivation did you have by using decision trees? Because I know that decision trees is really interpretable method, so maybe you use these rules which you obtain in each node somehow, something like that.
Well, I would say that the motivation was twofold. First of all, you always hear about how decision trees are very efficient and they can get a very good approximation of your targets. So that's one reason. The second one is that our model with decision trees can be, with some slight changes, can be transformed to consider not a decision tree but a random forest, which is even more accurate. And third, we try to write the decision tree model with this for the CSSP, and it was a linear program, so we were very happy, and in fact it's quite efficient to solve. So basically the reasons are accuracy in the machine learning prediction and quick solvability in the CSSP part. Thank you for your question.
Yeah, so I see. So it's just because it was easy to build your own model based on this decision tree structure.
Yes, basically it's we're confident that we will be able to obtain a good approximation and something which was easy to solve.
Yeah, great. I see some other hands in the audience. I think Manuel didn't ask yet, so maybe we can give the floor to Manuel's question.
Can you hear me?
Manuel? Yeah,
Hi.
great.
Hi, my question is for Gabrielle. Maybe I didn't completely understand the whole approach, so maybe this question you need to explain something to me again, because maybe I missed some detail. But I'm wondering, is the time for calculating, for solving the CSSP not amortized in the training time, or is part of the prediction time? Is it really important if we can move it to the training time, or is it in the training time? Is it really important? Because we could spend time offline training, creating the tree or the super vector machine model, but then as long as the prediction is fast, it's not that important that we waste this time in the training phase. Could you clarify this part? I maybe misunderstood some of the detail.
Yeah. So first of all, thank you for the question, and second, probably I was not clear, so sorry about that. Yes, the time to solve the CSSP cannot amortize, as you said, offline. So basically, what you do offline is you train your, like you create a predictor, and then let's say online, when a new instance arrives, what you do is you solve the CSSP, find the configuration for that instance, and then you use Cplex or whichever solver with that configuration to solve that instance. So that must be done online, and that's why seeing the results with the decision trees made me very happy this weekend, because the results arrived just this weekend. Because solving the CSSP in basically 0 seconds means that as soon as the instance arrives, you can find a good configuration and use any solver to solve that instance. Whereas when the CSSP solves the SVR formulation, you need some 10 or 15 seconds, so it's not as immediate to find a good configuration and then subsequently use it. So if you need to find a good configuration quickly because you need to solve a problem very quickly, then time may be a problem. Then of course there are some problems which are solved in, I don't know, 1 hour or 2 hours, then 15 seconds is to solve the CSSP is nothing. So it really depends on your application, but no, I wouldn't say you can amortize that time offline.
And if I may ask a quick question, is the time to solve the CSSP online dependent on the number of configurations that you have for training?
Yeah, definitely. No, wait. Not on the number of configurations you have for training, but on the number of configuration variables that you have. So if you imagine your data as a matrix, as tabular data.
Yeah. So it's the variables. It's not.
Okay.
That's what I was trying to think. So then it's already amortized because when you build the model. Okay, I think I understood. Okay.
In that sense, yes.
Thank you.
Right. Yes, in that sense, yes. You're welcome.
I think Juan had a question. I don't know. Maybe it's not relevant now. So
no, it's just that it was my previous question that I forgot to turn off the hand sign.
Oh, okay, great. No problem. So any question from audience? Maybe I can ask Jasone. Just quick question. Jasone, can you hear me?
Yeah.
I see. So I'm impressed by the models you developed, and actually my question is it possible, maybe you know the way how to do this, is it possible to find this contrafactual explanation without these optimization problems? So maybe you have some heuristics from any idea for that?
Yeah, I know that that's something that people have done. That supposing you don't know exactly what model you are using, then what you do to solve that problem, as you cannot use the structure of the model, is use some heuristics, and there's a lot of work on genetic algorithms and other other algorithms, heuristics, or using heuristics or meta-heuristics. Yeah.
Oh, okay. So it's it's already exist. Okay. So but your model, I think, because it's optimal, then the solution is better, but is by themselves, right? Okay. Okay. Thank you.
Thank you.
Okay. Okay, Manuel, I see your hand. Please go ahead.
Sorry, I don't want to. If I'm asking too much, please tell me to stop.
No, it's
but
okay.
I'm very much interested in Gabrielle's work. So I was wondering, because you show the in-sample and the out-sample results, and it was interesting that there was a huge difference between the two. I wonder, that's because
in the slides.
Yeah, in the slides. So I was wondering in the tables, I'm wondering whether by optimizing to optimality, are we kind of overfitting to the features that we use for building the model? Is this an issue, or you don't think that's the reason, or is not important in this context?
That's a good question, actually. Yeah, let me get to this slide. For example, yeah, this one. So what I found out just 3 days ago is that, for example, so what is really important to me is the out-of-sample instances, because in the in-sample instances, what you do is basically, it's as if in machine learning you trained your algorithm on the training set, and then you test it on the training set. So I expect our approach to work better on in-sample instances and worse on out-of-sample instances, which is what happens. As you see, like for example, the number of wins is less in the out-of-sample instances than the in-sample instances. But then with trees, something weird happens. Like trees are very, very good with out-of-sample instances, so with instances that are never seen during training, and they are worse than SVR in sample instances. So this could maybe tell that, I don't know, trees, maybe they generalize better in out-of-sample instances, or maybe SVR tends to overfit. But since that, I mean, overfitting is a definition of machine learning. Here, what we are measuring is not the results of the machine learning predictor. It's the results on the CSSP given by some machine learning predictions. So I would say there are some conclusions to be drawn, and what is expected is that in-sample instances are easier, that they allow to find a better CSSP solution than out-of-sample instances, and I'm very happy when on out-of-sample instances something good happens. I don't know if that answered to your question.
Yeah, I think it's interesting. I still don't not fully. I think there is more research, there is more analysis to do to fully understand why there is this difference between SVR and DT, and I don't completely. Yeah, but I think it's yeah. I think it's a good answer.
Well, what I can say and what is hidden in the slides is that in the purely machine learning results, decision trees have a slightly higher generalization. So I would expect that a predictor which gives a better approximation of p-bar also has better CSSP solutions, which is exactly what happens here in the out-of-sample instances. In this table and in the table with the primal gaps and the feasibility measures. So maybe there's some correlation with that.
Yeah. Okay. Okay. Thank you.
If you have any ideas, please write to me. It's
well, the thing is that I mean, decision trees are as long as that's the reason why random forests exist. That decision trees are tend to be understood as being tend to overfit if you don't limit the growth of the tree too much. So that's why I was finding this result very interesting, because you found the opposite here, which
actually here I didn't use this random forest. I used this.
Yes, but the opposite in the sense that I would have expected support vector machines to overfit less, but maybe my intuition is wrong. But it's interesting. Yeah.
Okay, thank you very much. Great to have so many questions. So we want to close the session by thank you all to the speakers and also to our audience for being here today. And well, you have enjoyed
Thanks to
a
the
lot.
organizers as well.
Thank you. And well, we see you next week.
Yes.
Great.
Looking forward to it.
Thank you, Cristina. Thank you, Xenia.
Thank you.
Thank
The
you.
video will be.
Thank
Thank
you.
you all the presenters.
Yeah.
Bye-bye.
The video will be on YouTube.